Now, the title of my talk is Climate Policy When Emotion Meets Reality, and it's just a bit of scaffolding to help me work my way through a set of points that pertain to the unusual case of CO2 as an environmental policy target. So those of us who've been in this for a long time, if we were going to date the beginning of the whole political process around carbon dioxide, it would probably be the 1992 Rio conference. So that's 32 years ago. And then there's the Kyoto Protocol, which was signed in 1997, although it didn't come into force for a few years after that. And then there's the Paris Treaty, which came into force in 2015. And notwithstanding all of the effort that went into those global diplomatic efforts, global CO2 emissions keep rising. And if you were to look at that chart, I just defy you to spot the years that those emission reduction treaties came into force. There are little notches along the way, but those are due to recessions. Those have nothing to do with the treaties. Now, another chart that helps establish the context is in the case of the US, but it's also true of Canada and European countries, CO2 per unit of GDP has been going down for a long time. So this chart goes back to 1960, and it's a roughly linear decline in the amount of CO2 released per unit of GDP. And that's happening because the economy is getting a little bit more efficient every year, more efficient in energy use, and also the balance between manufacturing and services changes a bit over time. So the economy is growing, but the CO2 per unit of GDP is just following its own agenda, its downward path. And the important thing there is, again, there are no real inflection points. You can't spot any of these big policies along that chart. Now, that is different from other types of air pollution. So the top chart there, this is data from Ontario, and you can see emissions from 1990 to 2014 of particulate, fine particulate matter, has been going steadily down. The bottom chart is emissions of sulfur dioxide. All during that time, the economy was growing. So the Canadian economy was growing, the Ontario economy was growing, but air pollution was going down. And it'd be the same story here. Most conventional air pollutants, especially since the 1980s, the levels have been brought down in absolute terms quite a bit, even though the economy has grown a lot. So when we talk about the case of CO2, it's in contrast to all these other forms of pollution. So the big question to ask is, what makes CO2 so difficult to deal with? Why is CO2 still going up as the economy grows while all these other pollutants are going down? So first, these are the 5 points I'm going to go through in some detail. Emissions mix globally. So unilateral action is useless. That's the leakage problem, as we call it. Those other types of pollutants, those are local pollutants. And so if you have a lot of local sulfur or particulate pollution, people see it right away and they want something done about it. But CO2 is really, it only matters at the global level as far as the climate issue goes. Second is the carbon cycle is large and slow, and so the benefits in terms of reducing the CO2 concentration in the atmosphere are going to be small and far in the future. Again, with sulfur, if you cut sulfur today, you'll see sulfur go down pretty quickly in your local air, but CO2 is not going to be the same. The third, a very important one, is that abatement options are very limited. The technology here is very different. The whole issue around how you would go about reducing CO2, it's not the same as particulates and sulfur. And related to that, emissions are closely tied to fossil fuel use, and it isn't really possible to decouple them. And that means that the CO2 control agenda cuts into the agenda around economic growth and development. And that's where the economics dictates a very different resolution of this issue. And then finally, the damages, if we're going to do cost-benefit analysis, we have to know what we're getting if we incur all the costs of reducing emissions, what do we get for it? Well, the damages that are being talked about associated with CO2 emissions are extremely uncertain. They're not measurable even in principle, and the estimates that we see are often grossly exaggerated and obviously exaggerated. And so that means it's a very difficult case to make on cost-benefit grounds. Okay, so those are the 5 points that I will go through. First of all, emissions mix globally. Everyone's responsible for a bit, some places more than others, but still, if you are going to reduce CO2 emissions in any meaningful way, you have to do it at a global level. It doesn't really matter what Canada does on its own, for instance. No one country can change total emissions. And that leads to leakage problems. The term leakage is what we use in economics to address the fact that when one region cuts emissions, typically the emissions don't disappear, they just move somewhere else. So if the US or Europe, well, taking the steel industry in Britain, for instance, so Britain has lost a lot of its industry, but especially its steel industry, to reduce emissions ultimately. But it doesn't mean those emissions just disappeared. That production activity just moved to India and China. And if anything, the same amount of steel production causes even more CO2 emissions in places like India and China because they have a much more carbon-intensive energy system. So if one region cuts emissions by, let's say, 10 megatons, and 10 megatons worth of new emissions appear somewhere else as a result, then we would say that's 100% leakage rate. Now, economists have put a lot of work into estimating leakage rates. They vary based on industry and the regional pairings. They've been estimated anywhere from 10% to 130%. There was a couple of studies that came out about 8 years ago looking at the Kyoto Protocol specifically and concluded that the Kyoto Protocol had a 100% leakage rate. So any emission reductions that happened in the compliant countries was fully offset by emission increases in the non-compliant countries. So it was a wasted effort in that sense. Okay, the second point about the carbon cycle. This will probably be familiar to a lot of people here, but I do this talk for, among other things, my students. So the question, what do we get for it if we comply with these treaties? So let's suppose that we had full compliance with Kyoto or Paris. All that's going to happen is a slight slowing down of the rate of accumulation of CO2 in the atmosphere. So we get to the year 2100 concentration. We don't prevent that concentration. All it means is we get there a little bit more slowly. We get there in 2105 instead. So whatever bad things you might think is going to happen from the concentration of CO2 that we were going to hit in 2100, we're still going to experience them. It's just a couple of years later. Meanwhile, the Kyoto Protocol, even though, as I'll show, it has so little effect, it was too costly to implement. And very few countries complied with their Kyoto obligations, including Canada, I must say. The various governments that made a big deal about, isn't Canada wonderful? We ratified the Kyoto Protocol. It was a Chrétien Liberal government at the time. They ratified it. The government commissioned some studies. What would it cost if we actually complied with it? The costs are way too high. It went on the shelf, and that was the end of it. Even Japan didn't comply with the Kyoto Protocol. Okay, and as far as Paris goes, it's a similar story. Countries are not on track to meet Paris commitments, although some places like the US, your emissions did come down, but not because of signing the Paris Treaty. It was more to do with the fracking revolution and the drop in the price of natural gas. So this is a graph from a study that was published by climate scientist Tom Wigley many years ago, looking at the effects of the Kyoto Protocol. And the bottom chart is the one I want you to focus on. So this top graph, that top black line, that's a projection of what the CO2 level will be in the atmosphere if there are no emission control policies. Not necessarily an accurate forecast, but it's the base case that he works with. So that's getting up to about 700 parts per million by the year 2100. And then he looks at a bunch of scenarios around compliance with the Kyoto Protocol. So I'll move on here. So that top line is without the Kyoto Protocol. To see the effect of the Kyoto Protocol, that's the next line down. That's the dotted line underneath it. And as you can see, there's barely any difference. That's full compliance with the Kyoto Protocol. The other lines are what happens if you not only have the Kyoto Protocol, but a whole bunch more subsequent treaties after that. So I'm going to zoom in a bit here. The effect of the Kyoto Protocol is that the concentration you would get in, say, 2095, you get there a couple of years later. So basically, for all the costs of the Kyoto Protocol, you haven't really changed the outcome at all. For the Paris Treaty, Bjorn Lomborg did a similar study. Here the chart is in terms of the projected temperature change. So the red line at the top is in this model scenario, and again, it's the scenarios, not necessarily a forecast. The top line is the red line. That's what happens if you don't do anything. And then the blue line underneath it, I don't know if you can even see the difference between them, but the blue line underneath it is just Paris on its own. So everyone complies with the Paris Treaty, but then it expires and isn't replaced by anything. If Paris expires, and then for the next 70 years, countries just keep on complying with it, that gets to the green line, which is 0.17 degrees as of 2100, 0.17 degrees below the top line. So again, this is the issue that because the carbon cycle is so big and so slow, it's not like particulates, it's not like sulfur, where if you cut emissions today, you see the change tomorrow. If you cut CO2 emissions, you're not going to see anything for decades, and even at the end of the century, you get very little effect. Now, this is going to matter when economists look at this issue, because we want to know, all right, we're incurring all these costs, what do we get for it? Well, all we get is this tiny little change 100 years from now, which discounted to the present is worth very little. So on the benefit side of this policy, the numbers just keep falling to extremely small numbers. Okay, so notwithstanding the notion on the part of many activists that it's in our power to stop global warming or address climate change, the benefit of these policies is the discounted value of a slight delay in reaching CO2 doubling or whatever the outcome was going to be in the absence of action. So this means the whole language that people use is all misguided. When I hear politicians in Canada and elsewhere talk about it's essential to stop climate change or even take action on the climate, it's obvious that they haven't really understood what we're talking about here. There's no action that we can take on the climate. And the demands that activists make, they're not meaningful because all the emission control policies that we ever talk about wouldn't change the outcome. It would just change the timing of the outcome by a small amount. Okay, nevertheless, let's suppose we decide we are going to reduce emissions. What are the abatement options? Well, they're very limited. So CO2 is closely tied to fossil fuels, of course, as you know. There are no scrubbers available for CO2. So in the case of sulfur dioxide, notwithstanding, I know there's the discussion around the acid rain treaty. There was a pattern of exaggerating the effects associated with that. But nevertheless, on the economic side, it turned out it's not all that expensive to put scrubbers on the smokestacks that capture all the sulfur, or virtually all of it. And when they capture it, it's set aside as a solid. It emerges from the scrubber as a solid or a slurry that can be reused or disposed of. Same with particulates. It emerges in a solid form. You can extract the CO2 from a smoke stream coming out of a power plant. It's expensive to do it, it's difficult, but it comes out in the form of a gas. So then what do you do with the gas? Well, you could release it, but then, of course, that defeats the whole purpose. So all that people have been able to think of is, well, there are some possibilities of putting it into a saline aquifer, but that's very limited in application, or pump it underground. So these carbon capture systems envision taking the CO2 out and then pumping it deep underground. And we do that in Canada. Some of that is actually commercially viable because in depleted oil fields, the CO2 that they pump in can increase the pressure and get a little more oil out. Kind of ironic, I suppose. But we also have underground caverns now that are being filled with CO2. But that is very expensive. It takes a lot of energy to pump the CO2 underground. And it's applicable only in a few locations. This is not something you could just do everywhere there's a power plant, just put a CO2 capture system on it. And even if you do, you're going to use up a lot of the energy from the power plant just running the pump to get the CO2 underground. So for all practical purposes, there is no catalytic converter for your tailpipe. Catalytic converters are those miracle devices on a tailpipe that drastically reduce the pollution that comes out of your motor vehicle. Even though the number of cars on the road and the amount we drive has gone way up over the past 100 years, but since about 1970, motor vehicle related emissions have gone way down. And that's because of catalytic converters. There's no catalytic converter for CO2 though. So the only option is to cut fuel use. That is the only option for large-scale CO2 emission reductions. Now, people do talk about energy efficiency. That's a common one that politicians like to retreat to. They don't want to. They don't want to tell people you're going to have to stop using fossil fuels. So then they start throwing a lot of money at energy efficiency programs. You know, home insulation, change your light bulbs, that sort of stuff. And this is all going to save the climate. That gets into. Well, the first problem is it's only weakly connected to emissions. So in Canada, in Ontario, where I come from, we don't use fossil fuels very much for electricity. Most of our electricity comes from nuclear and hydro. We have a few natural gas plants for peaking, controlling the peak demand. But so electricity efficiency measures in Ontario don't have any real connection to greenhouse gas emissions. But the bigger problem is called the rebound effect. So the rebound effect is a notion in energy economics that when energy use becomes more efficient, people use more of the appliance. So if you don't have very good insulation in your house, and it's really expensive to get your house up to, say, 60 degrees, and then you insulate your house. Now it's a lot less expensive to get your house up to 60 degrees. So what do people do? They heat their house to 70 degrees. So some of the savings in energy use are offset by the increased consumption. Same with the switch from incandescent to LED light bulbs. People discover, well, the LED light bulb hardly uses electricity, and the electricity is much cheaper, so I'm just going to leave the light on all the time. So this rebound effect, again, and something that's been studied by economists. This was a paper not too long ago, in 2021, by some colleagues of mine. And they looked at, for the US, some long-term data, used time series analysis to estimate the size of the rebound effect. In other words, the extra energy consumption caused by improvements in energy efficiency. And the answer is, after 4 years, rebound is around 100%, which implies that in the long run, no energy is saved. So for all the money that goes into energy efficiency programs like this, and there are lots of studies in this same genre, economists have shown you're wasting your time. I mean, if a better product comes along, that's fine. If new and improved light bulbs come along, that's great. But mandating energy efficiency is not going to address the CO2 issue. Okay, so if emissions are tied to fossil fuel use, that means they are tied also to economic growth. So let's look at the IPCC high emissions growth scenarios. And you saw in Cork's talk this range of scenarios that the IPCC puts out. Looking at the future, maybe emissions won't grow too quickly, but maybe they'll grow very quickly. And in the IPCC models, that means there's a lot of warming. Well, how do those emissions grow quickly? They only grow so quickly because there's an assumption in the scenario that the economy grows really quickly. So in these high emission scenarios, you do get potentially several degrees of warming by the year 2100. But developing countries become almost 70 times wealthier by 2100 than they are today. And that's the part that when they talk about the high emission scenarios, they leave out the fact that this is a spectacular growth story for the world. So putting it a different way, the high growth path implies developing countries achieve an annual average per capita income of almost $70,000 as of the year 2100. That solves every development problem known to humanity, and it involves some warming. So you think of every other problem that we're dealing with due to hunger and starvation and poverty, they're all fixed, and we have a bit of warming. Now the IPCC has a term for that. That's called the worst case scenario. However, well, it would be nice if we get that much income growth. We are not going to get high growth emissions in the way that the IPCC keeps talking about. There is, and again, Cork alluded to this, the IPCC has a long history of over-projecting emissions. So here's a graph from a paper a couple of years ago. The authors of this paper buried it in an appendix, and it was kind of peripheral to another point that they were making, but I think this is an absolutely fascinating graph. So this, on the vertical axis, it shows the concentration of CO2 in the atmosphere. The graph goes from 1970 to about 2015. And the thick black line is the observed concentration of CO2 in the atmosphere. And what you see, these fan-shaped collections of lines, these are projections put out by the IPCC and affiliated groups in every decade of the coming change in CO2 concentrations. Now the blue one here, I don't know why it starts below the observed levels. You just mentally move it up a bit to line it up. But you'll notice that of this whole range of concentration rates, only the bottommost one resembled reality. So, okay, well that was an early guess. Can't fault them for getting that wrong. But now let's go forward to the 1980s. And what have they learned? Well, they did exactly the same thing. They put out a range of projections. And again, the bottommost projection ended up being the only correct one, and all the others were way too high. Okay, well, surely they'll learn next time, right? So then the next time, it's the same thing. Every time they put out a batch of projections, they have this range, and the only credible one is at the bottom of the range. And then the upper ones are projecting way too much growth of CO2 in the atmosphere. And that continues right up to the most recent batch, the RCP scenarios, the SSP scenarios, and now a whole new scenario writing process is underway, and they're just gearing up to do exactly the same thing again. When policymakers see these projections, what happens is the focus is all on these worst case projections. And then they start thinking, well, we don't want to have that worst case outcome, so we're going to need a whole lot of policies. And if we implement a lot of policies, maybe we can get from that worst case top end down to the bottom end. And the point of a graph like this is, you're already there. You don't have to do anything. You've never gone anywhere except on the bottom end of these scenario ranges. I did some work on this about 15 years ago with a grad student. We looked at this previous batch of scenarios, and it was easy to show the top end, the top half of the distribution was impossible. What I didn't expect was that they just keep repeating the same mistake, but it aids them rhetorically in trying to scare people. Another issue potentially related to this is temperatures are obviously rising less than models project. Now, there are a lot of models and a lot of climate models, and they put out hundreds of scenarios. So this graph on the left I think I got it from Roy Spencer. I can't remember now who put it together, but this is sea surface temperatures, and you can see the black line, that's the observed sea surface temperatures. And this is the range of model, and these aren't projections, these are hindcasts. So they get to peek at the answer before they run the model, and they still get it wrong. And so you can see there's way too much warming in the model simulations. So there's a bit of warming in the sea surface temperature there, but here again, most of what the models are doing is taking the observed greenhouse gas emissions and concentrations and putting up way too much warming. This is from a paper John Christie and I did. This is the global lower troposphere. In that paper, we showed statistically every single model is over-predicting the amount of warming in the lower troposphere. Over the satellite record, we've also used the balloon record back to the 1950s. It's the same story. The models systematically overpredict the amount of warming, and then this is a chart from a paper by Nicola Scafida in Italy, looking at surface temperature records. This is the black line is the Hadley Center record. The panel on the left, that's if you take the climate models with the lowest climate sensitivity, the ones that the IPCC doesn't really like to emphasize because they project very little warming over the next century. Those are the only ones that match the historical data. The medium models and the high sensitivity models, as you can see, they just don't get the past right. They have too much warming in them. And that means they're going to project too much warming. Okay, so thinking again, in the economic sense, I've been talking about why we're unlikely to reduce CO2 emissions in any large sense unless there's a miracle in technology. You know, if someone comes up with cold fusion tomorrow or something like that, okay, all of that might change. Or if someone invents a CO2 scrubber, that might change things as well. But then we start asking, well, why would we want to control CO2 in the first place? Like it's a natural part of the atmosphere. It's part of our respiration. It's obviously good for plants. And prior to the climate issue, nobody thought about regulating it. It just wasn't a problem we were concerned about. You've seen some mention of the issue of the greening of the earth. This is well established in the scientific literature that the earth has been getting greener, a great deal of additional leaf area being detected from satellites, and about 70% of that is attributed to the extra CO2 in the atmosphere. And so you've got a global pattern of greening taking place. This also matters for agriculture. Now this graph, this is in a paper that I've been working on for the last few months. It's under review at one of the Nature journals. The Biden administration recently hiked its estimated social cost of carbon. So the social cost of carbon is the term that we use to describe the harm from CO2 emissions. And they dramatically increased that estimate. And a big driver of that was a study that said global warming is going to seriously harm agriculture over the next 100 years. It'll globally cut into all the major crop types. And the study that came up with that, they used the same data set that a study 3 years earlier had argued, well, the CO2 fertilization is basically going to fully offset any harm from temperature increase. So they didn't project a big reduction. So I wanted to know, why did these two studies use the same data but get very different answers? So it took a lot of digging. I finally got the data, and I reproduced the second set of results, and that's the blue line that you can see here. So these blue lines, they're showing, so this is for maize, rice, wheat, soybean. What happens warming in degrees, you can see the global yields are all going down, and especially soybeans really falls off a cliff. And so plug those into a global trade model, and they get these big costs from declining agricultural productivity. But in their data set, what I noticed is about half the observations were missing, and it was the CO2 amounts were missing from a lot of the big chunk of the data set. So I was able to go back to the underlying sources and recover the CO2 measures and stick them in, get the data set back up to size, reran the same analysis, and that gives the green line up here. So now, instead of these big crop losses, it's basically a washout. There's no net loss in agricultural output. So I thought that's kind of interesting. So I sent it off to the journal that published the first paper. And well, they said this would be of no interest to our readers. Sorry, we're not going to review it. But then they said, we have a sister publication. You could send it there. So I said, okay, fine, send it there. After a couple of months, the paper was rejected. I got the reviews, and the reviewers were obviously hostile, very argumentative, but they also made a lot of mistakes in their reviews. So I wrote the editor back and I said, look, these are the errors in the reviews. You should have given me a chance to reply to them. So the editor said, all right, we have an appeal process. You can fill out this form, supply some documentation, you can appeal the rejection. But, they warned, we rarely accept appeals. So I filed the appeal. 2 days later, I heard back, we've accepted your appeal, and you can submit a revised version of your manuscript taking account of the reviewer comments. So that went in a couple of weeks ago. I'm cautiously optimistic. But if they reject it, I'll send it somewhere else. I'll get it into print eventually. Okay, now, this is an economic point that I have to emphasize. My students often get this wrong too, measuring the benefits of abatement. So let's suppose that we could count the costs of global warming if there were no abatement policies anywhere. This is what governments like to point to when they say why we need to do climate policy. But that's the wrong measure. So what we then need to do is say, what are the costs of global warming if there are abatement policies? And it's the difference between the two. That's the appropriate measure. But then once you frame it that way, you realize, how on earth would you even measure that difference? So then we get into when people are going to tie bad weather events, for instance, to CO2 emissions. As you've heard, all these weather measures, even the IPCC isn't claiming that there are trends in them or that they can link them to CO2. Hurricane frequency, hurricane intensity, the data doesn't show a trend upward. In the case of precipitation, we have very good records in Canada, and even our Environment Canada department, they don't claim there's an upward trend in extreme precipitation. But suppose there was. Well, then you have to ask, okay, if there had been 10% less CO2 emitted back in 1963, how would today's weather be different? Well, I realize that there are people who will claim that they could give you an answer to that question. But the fact is, it's absolutely impossible to say. You're up against all the problems of turbulence and chaos and all the computational difficulties. Yesterday, Navier-Stokes was mentioned. That's in there as well. There is just no way to come up with a credible answer. By the same token, if we cut CO2 emissions today, there are still going to be hurricanes and floods over the next 100 years, and droughts and storms and everything else. So you'd have to be able to ask, what's the effect of emission cuts today on all of those future phenomena? It's impossible to say. It's not, you can run a model and come up with an estimate. It's just there's no credible estimate that you could offer. So if we can't identify the changes, we can't put a value on them, all we can say is they'll be small and they're going to happen a long time in the future. Okay, so where does the IPCC's confidence and attribution statements come from? Well, it comes from this paper from 1999, Checking for Model Consistency in Optimal Fingerprinting. Optimal fingerprinting is a method that climate scientists have used ever since the turn of the century for tying observed changes in the climate to CO2 emissions. It was a special purpose method developed by Miles Allen and Simon Tett in 1999. It was based on earlier work by a guy named Klaus Hasselmann, who framed the CO2 influence detection as a signal processing problem, and then these guys re-expressed the same thing as a linear regression problem. Unfortunately, these guys aren't really trained in statistics, so they proposed this regression model for doing fingerprinting to identify the role of greenhouse gases in observed weather changes. in their paper, they claim that their method automatically satisfies something called the Gauss-Markov conditions, which are essential in statistics for proving that your method is giving unbiased and consistent answers. And they also proposed a brand new test no one had ever seen, that if you run the test, it tells you your model is okay. None of this was ever checked by statisticians or econometricians until I checked it. And so I published this comment in the same journal, in Climate Dynamics, where I showed that Alan and Tet had made some mistakes in their math. They made untrue claims about their method. They mischaracterized the Gauss-Markov conditions, and their method automatically fails the Gauss-Markov conditions, which means we have no way of interpreting what they're even showing. And the test that they propose, the residual consistency test, is meaningless. So we can't have any confidence in the accuracy of the results. The wording I used, I tried to be polite, but as strong as I could. Confidence in the results of the 1899 methodology rests on their claim that it satisfies the Gauss-Markov conditions and thereby yields unbiased and efficient coefficients, and that as long as the residual consistency test yields a small score, the variance estimator is valid. These claims are untrue. 1899 omitted a key necessary condition for the Gauss-Markov theorem and misstated the others. The way the method is commonly used, the Gauss-Markov conditions automatically fail. The omitted Gauss-Markov condition has never been mentioned or tested in the optimal fingerprinting literature, and hence, there is no assurance past fingerprinting results are unbiased or consistent. Residual consistency test values provide no assurance on this point. So what I argued here is everyone who's used that method, which is everyone in this field, has been using a method that generates meaningless results. We have no idea how to interpret their results, and they certainly didn't prove the case. So Global Warming Policy Foundation in the UK, they put out this paper by me, which is a non-technical explanation of this whole field, or this whole issue. I sent my paper to Alan and Ted. I sent them a draft early on. They didn't get back to me on it. But when the paper was accepted at Climate Dynamics, I then contacted them and I said, I'd really like it if you guys published a response when my paper comes out. So I will hold it back from publication if you want, while you guys write a reply. So I waited a few days. Finally, Simon Tet wrote back and said, I don't think we're going to get around to it anytime soon, so you just go ahead and publish your paper, and it's good to have this debate. Well, it's 3 years later, and they have not replied. And I don't think they will ever make a reply. Miles Allen did make, he was contacted by an Epoch Times reporter, and he made some flippant remarks about how, well, we've moved on, we use a different method now, which isn't actually true. But anyway, so it's out there. I've published 2 papers since then that show not only are the results meaningless, but they're systematically biased towards overstating the size of the CO2 effect. They're biased upwards in particular. And again, no response from the other side. All right, so nonetheless, what if the IPCC models are correct? Well, some people would say that's the end of the world, that we're facing a major extinction crisis. And then you get a bunch of crusty old deniers like this group. They're going to say something different. So this is from a paper I read a little while ago. Over the coming century, for most economic sectors, the impact of climate change will be small relative to the impacts of other drivers. Changes in population, age, income, technology, relative prices, blah, 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 will have an impact on the supply and demand of economic goods and services that is large relative to the impact of climate change. All right, now, what kind of crackpot organization would say that and expect us to believe it? Well, that's from the 5th assessment report of the IPCC, Working Group 2, Chapter 10. One of the few places where a group of economists get involved in the IPCC, that was Working Group 2. They did a detailed survey of all the projected effects, assuming the models are correct, and they said, okay, well, there'll be some changes, but guys, those are pretty small compared to everything else that the world's going to be dealing with. And so that was their conclusion. Oddly enough, did not make the press, but it is in the report. Okay, so another issue about using the economic models is you have to assume what's the climate sensitivity. So these integrated assessment models that economists use, that William Nordhaus won a Nobel Prize for, these are the models that keep coming back and saying, this is not a big enough issue for us to really worry about. But they use equilibrium climate sensitivity, but they take them from the climate models. So a couple of years ago, with some co-authors, including Kevin Diaratna at the Heritage Foundation, we wanted to know what would happen if we switched to the empirically estimated climate sensitivity numbers. Because there is an empirical literature that tries to estimate climate sensitivity instead of just going with what's in climate models. So the social cost of carbon estimates at the time looked like that black line there. When we switch in the empirical estimate, run the same model, the social cost of carbon collapses to very small numbers. And so that means if you're going to do this as a cost-benefit analysis, even if you use the black number, actually, Nordhaus's point is, for the most part, we just live with global warming. We're never going to eliminate CO2 emissions, and it would cost way too much to try. We just have to learn to live with it. We'll eliminate the lowest value CO2 emissions over time, but then with the additional wrinkle of the change in equilibrium climate sensitivity, that further demolishes the cost-benefit analysis. Okay, so the points. Emissions mix globally, so unilateral action is useless. That's the leakage problem. The carbon cycle adjusts very slowly in response to even large emission changes, so we're talking about far future outcomes. Abatement options are very limited. Emissions are tied to fossil fuel use, which is essential for economic growth and development. And the benefits of the policy are unmeasurable, and attribution methods are biased and exaggerated and all the rest. So this is why nothing happens on CO2 emissions. It's not because there's some evil conspiracy of deniers thwarting action at the global level. It's because the facts just don't support the action. So it also means that this emissions path is a rational response to the underlying scientific and economic realities. And climate advocates, including the major institutions of science, are in total denial of all of this. They've got access to all this same information, and yet they keep calling for radical action of some kind, and they keep expecting things are going to look different. So you can guess how this is going to end. All right.
Great presentation. I love all your work, but I have two questions, I think. One is, let me give you both questions and you can answer how you like. One is, why do you use the term pollutant in reference to CO2, given that it's not a pollutant? I assume you're just acquiescing to some other force, but you tell me. But
I try to use emissions rather than pollutant, but yeah, sometimes I slip up.
Yeah, okay. And then the other is, have you, I don't know if you're familiar with the paper by Koutsayanis. He's done two recent papers, one called Hens and Eggs, and the other, I forget the title. It's a long scientific title, but what it concludes in the paper is that the isotopic evidence in the atmosphere for CO2 shows no correlation with human emissions since the Little Ice Age. None, zero. Have you looked at that study and the data and done any analysis?
I've seen some of Demetris's work over the years, and those papers, they're on the list of papers I'd like to read, but I haven't got to them yet. But I should. Some of like the hens and egg problem, other people have addressed that in the ICE Core record, and it's a pretty obvious story there that, as you saw in the last presentation, the order is backwards. But his other papers, I haven't had time to look at those yet.
I have a question regarding your projection, the various projections that are made, where you at one point you're suggesting that the third world incomes and prosperity will dramatically increase over to the next to the end of the millennium, But one of the things that happens historically is for industrialized countries is that the population expansion rate dramatically drops once the country becomes affluent.
Yeah.
The question is, and most of this, of all these huge growths that we're seeing, is simply due to increased world population.
Right.
So the question is the associated population growth or drop included in these projections?
Yes and no. So you're right. As income grows, even the low-income countries with high birth rates, their birth rate is projected to fall. Per capita CO2 emissions have barely changed in 50 years. And so this is what got me first interested in where these big emission growth scenarios are coming from, because all you really need to do to project CO2 emissions is get the population growth forecast, multiply it by per capita emissions, which will vary a little bit, but since 1970, that number has hardly changed at all. And if you do that, you get an emission projection that's, again, down at the bottom end of the IPCC range. To get their high end, they're imagining massive increases in per capita emissions, which are just impossible in terms of the underlying economics. It would just never happen. The fuel isn't there to support it. So in those rapid growth scenarios, the problem is with the way the IPCC puts their scenarios together, they start with outcomes and then they fill in the economic and population numbers that get them. But the population and the income numbers don't necessarily make any sense with each other. So they can have an outcome where you have income going from 1,000 annually per capita to 70,000 annually per capita, but that doesn't change the birth rate. So a reasonable scenario process would say, all right, that's totally unrealistic. But they have a back to front way of developing their scenarios.
Always start with the conclusions first.
Yes, yeah. They want to have that big spread, and over time it gets harder and harder to come up with rationale for the top end of it, but they don't give up. They keep doing it.
I'm looking at your entertaining cartoon, and I'm trying to get it. It's good, but I'm wondering: are you suggesting that the climate activists are trying to hunt reality, and or that it'll get them in the end?
Well, we're never quite sure in those cartoons what Elmer Fudd was looking for. The rabbit sort of appeared in his path, but he has this song about hunt the wabbit. But,
I think I have seen figures that the annual turnover of CO2 is about 815, I don't know if it's gigatons or what, but the emissions we're talking about are probably under 15. Where do they get the idea we're going to get so much CO2 as when there's all this exchange between photosynthesis and the ocean and all this stuff, that we're going to make such a huge difference?
So the standard model, and I don't have any specialized knowledge of this, but the standard model of the carbon flux is there's a massive amount that comes out each year from decaying vegetation, from ocean outgassing and other sources, and a massive amount that gets sequestered each year. So leaves grow on trees, and the ocean takes, in the cold areas, CO2 goes into the ocean, warm areas, CO2 comes out. And the story is those are huge fluxes, but they're roughly in balance. And the use of fossil fuels means there's a release of CO2 with no corresponding sequestration, except for the fact that once CO2 goes up, then all that greening takes place. So now there's more sequestration through greening. So this, again, these are just the standard numbers. the idea is about half of our emissions are automatically sequestered through extra greening. So we're only looking at dealing with about half, the need to deal with about half of total CO2 emissions if we wanted to zero out the net flux. Now, there is a problem that these are enormous numbers on the scale of, I think, 900 gigatons or whatever the unit is, against between 5 and 10 gigatons of emissions. So just small error bars on anything will dwarf what we're doing. However, we do measure the atmospheric CO2 concentration at Mauna Loa and other places, and that is going up. So it stands to reason that that's reflecting the use of fossil fuels.
Along the lines of this same issue, my understanding, is around the global emissions are around 900 gigatons a year, and human emissions are at like 37 gigatons and have been flat for several years. But we've had a few big perturbation events. One of those was the most recent, the current or most recent El Nino, which is estimated to be an additional 2 or 3 gigatons from the ocean. When that happened, if you look at the Keeling curve and other data sets, you can see the blip. Okay? We had a similar sized blip of 2 or 3 gigatons due to COVID.
Right.
That blip doesn't show up. We also have a recent blip in the most recent Keeling curve data. There's been a large year-over-year jump. That's a blip that doesn't make sense. All the while, it doesn't add up. You're seeing some blips and not others. And as you pointed out, you have this large thing versus this small thing, and there's large sinks too. Right. So I understand that the common, shall we call it consensus, is that half of the human emissions are absorbed. But in fact, I don't think we can really say maybe all of them are being absorbed. I mean, have you studied any of that data analysis?
No, I'm aware of what people talk about, and it's not something that I've looked at in any detail.
It's complicated. We'll take one more.
Thank you. Well, I'm just a medical doctor. I don't understand completely everything you're talking about. However, the idea of the population, it would seem to me, I can understand that when people get more affluent, et cetera, those societies, usually the birth rates drop. But when the birth rates drop because of intentional depopulation, as we're having in all these poor countries now through birth control, abortion, et cetera, that's being imposed upon them, it would seem to me that then they will be short on people and their economies will not increase. And we'll have the inversion problem that we have with, the elderly, the pyramid goes upward, and then you have not enough people to work and to provide for the economy, and then you have great migration shifts like we're having now, et cetera. So could you address that?
In the post-war period, we built these lavish social support systems, including public pensions and healthcare and all the rest, which were predicated on the idea that we'd have a small dependency ratio, meaning relatively small group of children and seniors, and a large working age population in between. And we're losing that. So the working age population is shrinking, the elderly population is growing, the population of babies is also shrinking. So this is a big problem for economic planners, trying to figure out how do we have a large enough working age population to pay for all these long-lived seniors who in their senior years cost an enormous amount to sustain. No one has figured out a very good answer for that. And also, if we don't have we have immigration is a possibility, but is not necessarily the answer, especially because a lot of countries bring in an age cohort that ends up being a lot like the profile that's here currently. We will allow for family reunification, so the young working age couple arrive, and then a few years later they get to bring in their elderly grandparents, and so we're back to the same problem as before.